Our next speaker is Lorenzo Maccone, and he's going to speak about geometric event-based quantum mechanics, relativistic quantum spacetime.
Okay, great. Thank you very much. Thanks for organizing this great conference. It's been lots of fun. I had great discussions. So yes, this is joint work I did with Seth Lloyd and Vittorio Giovannetti. So this work has been going on for many, many years. And what I'm going to talk about today is basically a way to formalize time in relativistic quantum mechanics, a new way to do that. And why do I do that? It's because that allows me to introduce a quantum space-time that possibly could be used for cosmology. So when in the many worlds interpretation we talk about the quantum state of the whole universe, of course we need to introduce some kind of quantum space-time to do that, especially if we know that Minkowski space-time is not good to describe our universe. So, okay, I'll say something more about that. For people who are familiar with the great contribution by Don Page and Bill Wouters, this is essentially a kind of a relativistic extension of their mechanism for quantizing time, and it's non-trivial, as you will see. So the one foundational problem we have when we want to quantize relativity is the following. Basically, if you think about it, quantum mechanics talks about quantum systems, because if you look at the postulates of quantum mechanics, like a state of a quantum system is described by a vector in a Hilbert space, or the evolution of an isolated quantum system is described by a Schroedinger equation, and so on and so forth. So quantum mechanics talks about systems, while relativity really talks about events. That's the essential part of the theory. And the difference is quite obvious, but quantum systems are infinitely extended in time. They go from minus infinity to plus infinity in time, and they can be finite or infinite in space. They will be infinite in space if you're talking about quantum fields, but typically they're finite in space. Instead, events are finite in both space and time. So I would say that the main problem in joining these two theories together is that they talk about two different things. Of course, now, which is the most fundamental concept? Is it the concept of system, or is it the concept of event? What do you think? Event, okay. System. No such thing. Okay, great. So, of course, both in quantum mechanics, you have events, and in relativity, you have systems. But, I mean, in relativity, in quantum mechanics, systems are more fundamental, and events are derived notions, something that happens to a system, whereas instead, in general relativity, events are more fundamental, and systems are just a sequence of events. So this is how you have both concepts in both theories, of course, but they have different importance. Now, if you think about quantum gravity approaches up to now, they have been focusing mainly on taking systems as more fundamental, just because you are taking the quantum mechanical framework and just applying it to general relativity. And now what I'm proposing to do is to explore the alternative, take events as more fundamental and construct a quantum theory of events, okay? So this is the main idea. I mean, up to now, the talk has been very philosophical, and I think this is more appropriate to this audience. Of course, we have many technical results, and I'm going to talk about some of them. But just to make it clear what I mean by this difference, well, look at this graph on the left. You have the relativistic version of a system. It's just a timeline, a sequence of events. And if you think of how you would convert that to a quantum way of seeing it, this is a sort of a space-time diagram in which a single particle in two counter-propagating Gaussian wave packets interferes, and then the Gaussian wave packets go off to infinity. You see that there's a problem because you sort of have no trajectory in space. You see there is destructive interference at some points. You'll never find a particle, but there is no such thing in time. In time, the wave function is normalized at all time, which means that basically the trajectory, the particle exists at all time, but it does not exist at all positions in space. So there is very definite differences between the treatment of space and time in normal quantum mechanics. So trajectory in space are ill-defined in quantum mechanics. Why should we take trajectories in time to be acceptable? Now, to go beyond that, we need a Hilbert space for events and try to construct the quantum mechanics for events. And that's what I am proposing to do. So let's start with special relativity, deal with general relativity in the very far future. I don't know if we'll ever be able to do that. I mean, I've started discussing with David Bruschi about this. He's a relativistic quantum information person, and we have some ideas, but I don't know if we'll ever get anywhere. So in special relativity instead, things are much easier, of course. So now let's look at textbook quantum mechanics, and textbook quantum mechanics uses quantities that are time conditioned. For example, states, in the Schrödinger picture, they are states conditioned on time. There's the state of a system given that the time is t. And if you go to the Heisenberg pictures, instead it's the observables that are conditioned. It's the position observable given that time is t. And of course, this means since you're conditioning on time, you need a specified foliation just from the start, and they cannot be relativistically covariant. Covariant means that formulas look the same in all reference frames. That's what I mean, basically. So what about QFT? Well, okay, QFT uses a couple of tricks to recover covariance. Maybe I will not go through this. By the way, I'm not going to say that quantum field theory is wrong, of course. No, that's not my aim. I'm just trying to explore an alternative which gives the same predictions. Now, our approach instead will be to base everything on unconditioned quantities, and we call it geometric event-based quantum mechanics. Geometric because it's sort of like a space-time thing, and event-based because, of course, events are fundamental, quantum events are fundamental, and quantum systems are derived, as I will show you, like a quantum state for a succession of events in quantum space-time. That's what a quantum system would be in this framework. So, of course, what is an event? I mean, if you look at general relativity textbooks, it's kind of funny how they define events, but let's not go into that for reasons of time, and just define the bare minimum we need to define an event is that it has a position in space-time. But in quantum mechanics, we will also require some energy and some momentum, otherwise you cannot localize. Without energy, nothing can happen. Without momentum, nothing can be localized. So in a sense, we need two basic observables to define an event in quantum mechanics. This x bar, the over bar just means it's a 4 vector. So the x bar, which tells you the position in space-time, so also time is a coordinate of the event. And p bar is the energy momentum observable, tells you the energy and the momentum associated to that event. And of course, I'm going to impose the canonical commutation relations among these. And why do I do that? Because I just want the Poincare algebra, and in this way, by imposing these commutation relations, you get Poincare algebra. So this m mu nu is just, I'm not sure the name, it's the angular momentum, the relativistic angular momentum. So the spatial part is just the angular momentum, and the temporal part of this tensor is the generator of boosts. So you get the Poincare algebra, which is nice if you want a covariant theory. And then you can construct quantum states out of the eigenstates of position and momentum just by adding a probability amplitude. So this kind of state describes a universe in which you have a single event which has some probability amplitude for the event to happen at some space-time location, or that it has some energy momentum connected to it. And of course, as you can imagine, not all of these states are physical. So the physical states, following the Page and Wooter's mechanism, and also, of course, Dirac and other people, the physical states are the ones that satisfy some constraint. I will get back to that. But let me immediately say that, for example, the eigenstate of the position of space-time position is not a physical state because it describes an event. Think of, for example, a detection event of a particle that exists only on one space-time location. So this particle appears out of nowhere at some time, gets detected, and then disappears in nowhere. This, of course, is not a physical state. And so this kind of state cannot describe really anything physical, but so it cannot describe a quantum system. So you cannot construct a quantum system out of this event state, but you can use it, for example, to describe a measurement apparatus. And physical states, as I was saying, are the ones that satisfy some constraints, which are connected, of course, to the dynamics and to other systems, to other properties you want your theory to satisfy. And of course, once you have states, you can have amplitudes, wave functions, basically. But these are four-dimensional wave functions where basically you have a probability amplitude for the event to happen at the given space-time location. And you can go from the position representation to the momentum representation just through a Fourier transform in space-time. So this is nice. And the Born rule has the usual definition as a square, the square modulus of a scalar product. But, and so this gives the probability that the event happens at space-time location x bar. And it's just, as usual, the square modulus of the scalar product between the eigenstate of the observable you're looking at and the state of the system. But in contrast to the textbook Born rule, this is an unconditioned probability for finding the event in space-time position. Okay? So why do I put unconditioned in huge capital letters? Because the Born rule in textbook quantum mechanics instead is a conditioned probability because, for example, this is the probability to find some particle at position x given that time is t. So it's a conditional probability. And you can write it in the Schrödinger picture by putting the conditioning on the state, or you can write it in the Heisenberg picture by putting the condition on the observable. It doesn't matter. In both cases, it's obvious that it's a conditional probability, sorry. And of course, this means that textbook quantum mechanical probabilities are not covariant. Okay, they depend on the reference system, on the reference you're using. And typically, of course, no sane quantum field theory textbook is going to make that claim, although I found it in some minor textbook. But instead, it's very important that Jeb probabilities are indeed covariant because they are unconditioned on the space-time position. And, yeah, maybe I can say something very quickly about the uncertainty relations. Of course, once you impose these canonical commutation relations also on the temporal part of these vectors, well, you get an uncertainty relation also for the time energy part, x0. P0. And notice that this is a true uncertainty relation of the Heisenberg-Robertson type, whereas in textbook quantum mechanics, this is completely meaningless. I mean, time is just an external parameter, and this has been pointed out by many people. Since I'm in Israel, I should point out Asher Peretz, but of course, even earlier, Aharonov Bohm pointed this out. The time-energy uncertainty relation in textbook quantum mechanics is just basically a quantum speed limit, which tells you how fast, what is the minimum time interval, not time uncertainty, it takes for a system to evolve to an orthogonal configuration given some energy spread. Okay, but instead, in our case, we do have a time operator and we can construct, we can look at the uncertainty in the measurement of time at which the event happens, and we can construct a time-energy uncertainty relation. And of course, the physical rationale behind that is that you cannot localize an event in time unless it has some energy spread. I mean, if it has no energy spread, it's localized in time. And one nice thing also about this construction is that Lorentz transformations become very simple. It's just a unitary transformation on the state, just like Wigner's prescription on how to describe symmetries of a theory. And of course, the Lorentz symmetry is a symmetry of relativity, and you want it to be a symmetry of relativistic quantum mechanics, and in this case it is. It's just a unitary transformation. I'm not going to put the details. You can find them in our paper. We've worked out all the ways you can write this unitary transformation that describes Lorentz transformation. I should point out that in quantum field theory, Lorentz transformation are really very complicated. So basically, since you are quantizing, you are imposing canonical commutation relation at fixed time, you need to start from, you need to re-quantize from scratch when you want to do a Lorentz. I mean, you can do it, of course, but you need to start from scratch. You need to rerun the quantization procedure from the start. Or maybe this was one nice feature about our construction. Maybe you can go from quantum field theory up to Jeb, and then use the unitary I'm describing, and then from Jeb go back to quantum field theory. This connection from QFT to Jeb, I'm going to talk about in a minute. So this is a way to do Lorentz transformations using our framework. Up to now, I've talked about universes in which you have a single event, which of course is not very interesting. But if you have multiple events, it's not too difficult to extend the construction, especially if you have a fixed number of events, like a fixed number n of events. Then you just take the tensor product of the n Hilbert spaces for each single event, and you get a state of this type. Look at the wave function, and you notice that this wave function has n different times, okay? And this makes sense if you're talking about events, because each event has its own time of occurrence. It makes no sense if you're talking about systems. And indeed, there are papers, for example, by Dirac, in which he writes a wave function of this type, and then he kind of runs into some sort of trouble to understand what it means for a quantum system to have n events. And magically, at some point, all the events are made to coincide, and they just go away, and only one is left. I mean, this in Dirac's paper. Of course, if the number of events is not fixed, if n is itself a quantum number, then you have to escalate to Fock space. I mean, this tensor product of n Hilbert spaces is not going to help anymore, but it's not too difficult to extend the whole construction to Fock space. You introduce these creation operators, which create an event at space-time location x1. Sigma 1 is some internal degree of freedom, for example, the spin of whatever particle you want to describe. Remember, particle is a derived concept starting from event states of this type, but it can have additional degrees of freedom. And of course, the Born rule is going to give you the joint probability for all the n events to happen at space-time positions x1 through xn, and it's just, as usual, the square modulus of the wave function or some scalar product of an observable eigenstate and the state of the system. And of course, as I was saying, each event has its own time. So let me say 2 words about this Fock space, this weird Fock space. And it's interesting that you can have 2 different kinds of events depending on whether you put commutators or anti-commutators. You can just impose these commutators or anti-commutators to the creation and annihilation operators, and you get bosonic events and fermionic events. And of course, bosonic events will give rise to bosons when you take a state of a sequence of bosonic events, and fermionic events will give rise to fermions if you get if you take a state of a superposition of a sequence of fermionic events. And the nice thing is that the commutation relations you see here, you have a delta 4. It's a delta in space-time, not as usual in quantum field theory where you have a delta 3 at fixed time. Okay, so this really drives home the fact that this is a fully covariant formulation. And another thing I should point out is that this 4 vacuum that you are acting on with these creation operators, it's a different state from the 3 vacuum of quantum field theory, because the 3 vacuum basically, if you work in the Schrödinger picture, the 3 vacuum of quantum field theory, it says that there are no particles at some specific time, or in the Heisenberg picture, it's sort of like there's no particle at time t equals 0. So it's a ground state of some particle field. Here, it's the ground state of some event field, if you want. So it's really a different state. Perhaps you can get the 3 vacuum by sort of taking the 4 vacuum, applying the creation operator for the ground state, so for the 0 energy event, and taking only the spatial part of this. I'm not so sure, but perhaps this is a way to connect these 2. And of course, as I said, our idea is not to say that quantum field theory is wrong. Of course, quantum field theory is correct. It's just to find a different approach to relativistic quantum mechanics. So we want to see how these 2 theories can be connected. And as I was saying, the basic idea is to use constraint, as in the Page-Wooders formalism, in the Wheeler-DeWitt equation, Dirac constraint, etc., etc. So the idea is the following. You start from a single particle or single event wave function. You start from a single particle wave function in quantum field theory. So this is a conditioned probability, condition on time to find the particle at position x. And of course, you can have some internal degrees of freedom. And then you can construct a Jeb state for it, from it. So you promote the time from being a condition to being an internal degree of freedom, and then you write the state. Of course, when you do that, you're losing the probabilistic interpretation, just because you're taking a conditional probability and promoting it to a joint probability, and you would need to use Bayes' rule maybe, or some other way to do that. So, of course, when you do that, weird equality here says that you're really losing the probabilistic interpretation when you do that. But when you do that, you have a Jeb state which is describing basically the whole dynamics at all times of the particle seen as a sequence of events. So now this is representing a sequence of events. And then in order to write that in terms of some constraint equation, you can write this state which contains the whole dynamics as an eigenstate of some constraint operator, like K, which is the constraint operator. And of course, I was showing you the very simple example of a single particle, and we worked out slightly more complicated quantum field theory systems, for example, the Klein-Gordon fields, and this is the constraint you get, and there is a similar one for the Dirac field. I don't want to go too much into the technical details, but if you look into our paper, you're going to find them. So again, I want to stress that we, of course, do not claim that quantum field theory is incorrect. That's not our aim. We just want to give an alternative an alternative approach to relativistic quantum mechanics, in the sense that, in some sense, David was talking about in his talk. He was saying, "Oh, we shouldn't do that," but we are trying to do that. But alternative not in the sense that quantum field theory is flawed, but alternative in the sense that it's a different way to obtain the same result. So why do we want to do that? And of course, one reason is what David was advocating in his talk this morning. Maybe that will allow us to get a better ontology, because of course we know that, as he was pointing out, that going from the observations you can do in quantum field theory to going from the fundamental things you have in quantum field theory to observations, there's a long way to go. And maybe this approach gives a more direct way to go. And another hope, of course, is we know that quantum field theory is limited in the predictions it can give. Perhaps this approach might go beyond this limitation. That's, of course, my main hope. As of now, of course, I don't have any better results. I mean, I have less results than quantum field theory, much less. So I don't know if that's a good hope. I mean, it's certainly a good hope. I don't know if it's something that is true or not. Okay, so I was supposed to talk for half an hour. Let me conclude. So I presented to you this GEP, geometric event-based quantum mechanics, which is a new approach to relativistic quantum mechanics, where quantum events are taken as the fundamental entity on which to build all the rest. I mean, we're taking the cue from relativity rather than trying to straitjacket relativity into quantum mechanics. And of course, I've shown you how observables, Hilbert spaces, Fock spaces, bosonic and fermionic events, and hence particles arise in this framework, and then how to connect quantum field theory and the Jeb for the easiest situations you can get. So the non-interacting Klein-Gordon and Dirac fields. Of course, we're working on generalizing this, but this is as far as we have, I'm confident in speaking up to now. And the take-home message is, okay, a new approach to relativistic quantum mechanics. Our paper is here. Thank you. Thank you for your
We can have a short discussion on Lorenzo's paper for about 10 minutes, and then we're going to have a general discussion anyway. So, shall we start with David?
Thank you. That's fascinating. And I don't have any problem at all with trying to reformulate theories. I mean, you don't have any problem with anything anyone does. Everyone should do what they like. But in particular, I don't see any reason there shouldn't be interesting reformulation.
No. That was clear. Sorry.
Just to get some parameterization of how far the project's got so far, can you do interactions?
No. No, of course, that's the main questions. That's the main question. I mean, I've started to think about that, but of course, complexity diverges, as you know. So we started from the simple case first, and we worked out that.
Reasonably enough. Thank you.
Yes, thank you. I've long been fascinated by the very thing that you're trying to do, but I long thought it couldn't be done because a canonical commutation relation between time and energy is really problematic if the energy's got a discrete spectrum. So does your energy operator have a discrete spectrum? And if so, how can you have a canonical commutation relation?
Oh, no. This is something we elucidated also in non-relativistic quantum mechanics. So once you quantize time using the Page and Wouters approach, then time is not really a property of the system, is a property of the clock you're using to characterize your quantum experiment. So, of course, the clock has the problems you have, so you will never have an idealized clock. But the system Hamiltonian can have any spectrum you want. Okay? It's the clock Hamiltonian that you have to worry about.
Yes, but if you've got a canonical commutation relation between two self-adjoint operators, one of which has got a discrete spectrum, you're in trouble.
Yes, indeed. So in this case, the energy I'm talking about in the canonical commutation is the energy related to the event. Okay, it's not the Hamiltonian. You connect the energy and the Hamiltonian using a constraint. Okay, so the two does not have to match. That's the important thing. They even, as in his construction, they even might work into two different Hilbert spaces, and so they commute. So there's no issue at all in that case.
Okay, well, thank you.
I understand I haven't been very clear, but we can discuss and can show you.
Thank you for the excellent talk. I had the following question. So in the original Page-Wouters construction, different times are like different effort universes. In your construction, is every event in space-time like a different effort universe? So there's relative states relative to each event? And the other question was, you propose this exosystem with the canonical commutation relations besides the quantum field. Do you think it's possible to only use quantum field theory and the commutation relations of quantum fields to derive the same construction?
Sorry, I didn't get the second question.
Well, so as I understand it, you propose a quantum field and then another system with these x0, x2, x1, etc. observables that obey the canonical commutation relation.
No. The quantum field is that x is the position of an excitation of the field. For
okay, then I misunderstood. Yes. Right. Okay, so then, yeah, that answers the second question.
Yeah, it's like, I mean, it's not really specified in the theory what we mean by event, but one possibility would be like the detection event, where you will find the particle which is connected to this sequence of events, okay? So this could be like a detection event. But you can think of different kinds of events too. I mean.
Okay, thanks.
And okay, the other point. You were trying to make. sorry, it was about the Everett branches. I'm not sure because I've seen, especially in this conference, that people have different definitions of what they mean by branches. But I guess, sorry, I should go back. I guess what I'm proposing is a superposition where you have, this is an integral over space-time. So if you take the temporal part, you have a superposition over different times of these events. So I don't know, if a superposition is sufficient to define a branch, then yes, every time is in a different branch. Or if you need some decoherence, then you need to add some more structure to it. But yeah.
I think many don't like Copenhagen interpretation because they don't know when measurement happened. So I don't get here how I connect it to what I see around, because it seems that event. Another way for me of this objection that there are no events in quantum mechanics. You don't really know when detection happened.
Sure.
It's
okay, here
if we have time and the system exists forever, and the single universe event, it's not so. What is the connection to? Can you have some example when?
Okay. Yes.
Okay. What the event is, because this is my difficulty, I think, once I ask you, but I never understood.
Okay, so what an event is, that's a very, very difficult question in general. And it's funny that if you go to general relativity textbooks, you find two different definitions of events. And for example, in the Wald textbook, it says that an event is a point in space-time, and then he says space-time is the collection of events, okay? So clearly it's a circular definition, and this just means that it's a primitive concept. It's something that you cannot define based on something else. Or if you take the Thorne-Wheeler textbook, for example, then they define event as intersection of world lines, so it's a different definition. But of course, this kind of definition cannot be extended to quantum mechanics because you don't have world lines. So a general definition of event, I wouldn't know how to give, and I think I'm in good company with that. But to go back to your question, which is not necessarily a question about defining an event, but a question about measurements. Okay, so the way you can incorporate measurements in this framework is the way we did it in the Page and Wooters framework. So that was our contribution when we wrote this quantum time paper. And the idea is basically to introduce some ancillary systems which are represent like the measurement apparatus, and then use von Neumann's prescription and consider the measurement as some interaction between your system, in this case, this kind of sequence of events, and the measurement apparatus. So you would need to introduce an interaction with some external things. Of course, you need interactions to do that, and we don't know how to do that. But in principle, that's the way you would do that. And of course, that means that on one level, you have a complete unitary description at the level of the universe of the measurement thing, but on the level of the relative state or the observer, it would see a definite outcome. It would be on a single branch, okay?
So maybe it's even more difficult question. I was willing to understand on which when I have an experience, even in Bohmian mechanics, it looks like there is a disagreement, and probably you have formalism based on events. Will you say that after you'll get your interaction, the experience of an object, of an agent supervene on events, or it's supervene on something else?
Okay. Maybe we can discuss offline because I'm not really sure I understand the question, but I guess I would say that once in the many world formalism, you would connect this kind of state to some ancillary system through some interaction which selects some sort of basis, and then you redundantize, and the observer gets entangled, and in each branch of the wave function, the observer sees a definite outcome, a definite relative state, just because, I mean, it's the usual standard picture. It's not going to change because we introduced quantum mechanics of events. I would say it's just the usual picture I would use to describe measurement and perceptions in normal quantum mechanics. Normal, by normal I mean maybe many worlds, maybe not, depends on the definition.
Still, what is the status of event? It's beyond the quantum state? It's description of a quantum state? In many words, I say you have to make branching, and after the branching,
yes.
that experience supervene on the wave function of a branch. And in Bowman mechanics, I like that it's supervene on Bowman positions.
Right.
And in GRW flashes, I like that it's supervene on flashes. And
yeah, I would
say it's supervene on events, or you just events are just another.
Events. I would say exactly like you would say in many worlds on different branches. You connect the events to different branches depending on what you're measuring, right? So then the addition with respect to normal way of doing it is that now also time is a dynamical variable. So here you can also describe time measurements, which in normal textbook quantum mechanics you cannot do. So you get something more. For example, I have a paper in which I use this mechanism to describe time of arrival of particles at a detector. And I mean, you really have problems doing that in normal quantum mechanics, describing time measurements. But for the rest, if you want to measure anything else, it's just the same picture you would use elsewhere. So this picture does not bring anything more to the table, except the possibility of measuring time, that's all.
One more question. We'll stop with this paper, and then we're going to have general discussion.
Yeah, thanks for the talk, Lorenzo. My question was, if you think about, in your talk, you were making connection with the canonical quantization approach to field theory, but another approach is to make a path integral approach, where you look at functional integrals over fields. And there, the Lorentz invariance is very transparent. And so my question is, have you thought about trying to reformulate this way of doing it and making a connection with the path integral approach? Because if you could, that then maybe give you a path to include interactions, because it's very clear how to include interactions in a path integral approach. So if you can connect somehow your formalism to this integration over field configurations, that seems to be would be a fruitful next step.
Yes, thank you. No, we haven't tried it, but as I was discussing with David the other day, the path integral formulations, I agree with you, it's completely covariant, except when you say that it's a transition amplitude between two states. And when you have states, I mean, for example, in the Schroedinger picture, it's a conditioned quantity. The Heisenberg picture, it is also. So you kind of need, you don't need a foliation in order to calculate the path integral, but you need a foliation in order to define the transition amplitude between what and what. Because the initial state and the final state. To define those, so I'm not sure that I would agree with you that path integral would be a completely covariant, it's almost completely covariant. Maybe not all the way, I'm not sure.
Yes, could I just ask, just one other thing. You said at one point that in conventional quantum field theory, you have to quantize again for each different frame of reference and so forth.
Yeah, that's not necessarily true. I mean,
Well,
that's what you would do usually, right?
Okay, I mean, the typical view of what one's trying to do in relativistic quantum field theory is to find a representation of the Lorentz group in terms of self-adjoint operators, typically constructed out of the fields. But that does give you a representation of the Lorentz group. So, in other words, you can define Lorentz transformations all within a given.
Sure, but
Puzzled by what you said.
yeah, but the Lorentz transformations are not in quantum field theory. You do not Lorentz transform a state by applying a unitary to it. That is not going.
Applying a new what?
A unitary operator, which is a unitary representation of the Lorentz group. That's not going to work.
You're saying we do not have unitary representations of the Lorentz group?
Yes, we do have, but it's not that to go from one frame of to describe the state from one frame of reference to another, you apply a unitary to it.
But then it's not a unitary representation of the Lorentz group. I don't understand you. Lorentz group includes boosts. A unitary representation includes unitary.
Okay, so maybe I'm saying something wrong here.
Are you in agreement?
Okay, we're gonna go now to the general discussion. Thank you, Lorenzo.
Thank you.